University. Today I'll be talking about our work on explainable AI, more on the application side of things, and how we ground the deep neural network models, and how we use this grounding to further improve performance of such models. So the work I'll be presenting today is a collaboration with Andrea Zanino and Vittorio Marino from IIT Genova, Italy, Zhengming Zhang from Adobe Research, and Donion and Stan Sklarov from Boston University. So I'll start by motivating our line of research. And I'll start by saying that as AI systems are becoming very crucial, they're integrated into many, many crucial applications, it's also becoming very crucial to explain why they make specific decisions. And it may be very obvious why we want to explain why a model makes a mistake, but it's also equally important to explain why a model makes a correct decision. And one of the applications that's currently very heavily using deep neural networks is autonomous vehicles. And in autonomous vehicles, there's an action that is very important, which is pedestrian crossing, for instance. So we would like these vehicles to be able to, predict if there's a pedestrian crossing the road at any point in time. And so let's assume we're a company. We have a very challenging data set. On this very challenging data set, we are capable of predicting this action, that's pedestrian crossing, 99.9% of the time. The question becomes, is this system ready to be deployed or not? So we argue that it's not until we know why it's performing so well. So for example, if we have this scenario, we're capable of predicting all pedestrians in this data set that are crossing the road at any point of time. And let's assume that the reason the model is correctly classifying this action is because it's modeling the periodic motion of the legs of these pedestrians. And so now we obviously have a problem if the pedestrians look like this, okay, where their legs are completely occluded. And so in our work, what we do is we try to ground the evidence of a model's decision. So we try to see why the model made a specific decision. And also we try to use this grounding in order to further improve the model so that it doesn't make the same mistakes over and over again. Okay. So I'll start by defining what we mean by grounding. So we work with visual data, meaning we work with images and videos. So I'll start by showing what we mean by grounding a specific network decision. And then we'll talk about how grounding can be useful. So typically, in deep neural networks, what we have as input in visual data is either an image or a video frame. And so if we input this image and perform like a bottom-up inference in a deep neural network, we get predictions. And what we can do now is we can go in a top-down fashion and actually try to find which neurons fire in order to make this prediction and map this network structure or the firing of the neurons back onto the spatial image to see where the model was focusing when it made this specific decision. And so in this case, what we can do is we can ask the model, why did you predict zebra? Or why do you think there's a zebra in this image? And we would get something that looks like this, okay? So this is using one of the grounding approaches that use a top-down analogy, and this would be sort of the result or the explanation in the form of a heat map, where red means higher evidence and blue means lower evidence. We could also ask, even if the network predicted zebra, we can still ask what is the evidence of having an elephant in this image, and we would get a map that looks like that. Okay? So the beauty of these grounding techniques is that you could ask questions even if these questions were not really the ground truth. And I'll show more examples of that. And so how do we know why our deep models make certain decisions? This is a question that we were really inspired when we saw some of the misclassifications that our networks perform. So this was one video frame from the UCF 101 dataset. And the ground truth label for this video was a baby crawling, okay? However, when we fed this video into our model, this was the prediction. The model decided that this was a video of push-ups, okay? So if you carefully analyze the image, you might say, okay, the baby is in a pose that's very similar to a person performing push-ups, right? But how do we know that that was the reason the network made such a misclassification, right? It could equally just have been that in the training set, there was a person performing push-ups on a carpet that looks very similar to this carpet, right? That could have been the reason for the misclassification. And so if we had this sort of tool that highlighted or at least showed us where the model was focusing when it made this decision, that could help us in explaining why this image was misclassified. Here's another example, just to show you how these tools could be used to highlight evidence, whether or not this evidence is actually the ground truth label of the image. And so here we have an original image of a facial expression of a person, and the ground truth label for this facial expression is happy. Okay? So what we can do with these grounding tools is we can ask the network, why do you think this person is happy? And it sort of highlights the smirk over here on the left side of the mouth. And then you could also ask the model, what about this face looks neutral? And the model in this case decides that the nose is the part of the face that sort of contributes to a neutral action. Other examples where such explainability is using to bridge the gap between different domains. So in a lot of applications, you have a training domain, but then the testing domain is a lot more general, right? And so this is an example to show you how this explainability could also be used to bridge such gaps. So in this work, what we do is we train for object classification on a graphics dataset. So it's a dataset where the background is white, and then there's a graphics generated gray object in the middle. And then we test this model on images that are real images, taken with like RGB images, such as this one. So this is an example that shows an airplane in the hangars. And what we do is we test this image on the model that was trained on these graphics images. And obviously it gives an incorrect prediction, and it says with very high probability, this is a motorcycle, okay? Now when we look at the evidence as to why this model thought it was a motorcycle, it highlighted like a very non-discriminative metal part of the airplane, okay? What we did next is we retrained the model using a domain adaptation approach where the distributions of both domains were aligned. And then we made a prediction on the same image. We got the correct class with very high probability, and then we also used these grounding techniques to show the evidence as to why this was classified as an airplane. And now, as you can see, it's highlighting like a very discriminative portion of the airplane, which are the wings. Okay, so you can see that the explanation is usually in line with the predictions. I'll show you one example of one formulation that is used to produce these heat maps, if you like. So let's assume that J is a neuron that is closer to the classification layer, so it's a deeper neuron in the network, and let's assume that I is a shallower neuron, okay? The way we compute these saliency maps and these top-down approaches looks like this. So we compute the probability of A of I given A of J, and then we compute the saliency map, okay, the saliency value, the color of the pixel at a specific location, and we call that P of AI. So P of AI is basically the saliency value at this neuron AI, okay? And the way the saliency is computed is by multiplying this conditional probability by the probability of AJ, or if you like, the saliency also that was computed at neuron J, going backwards in the network. So that's for spatial saliency. We then extend this work in order to get spatio-temporal saliency. And let me define what the spatio-temporal saliency problem is. So let's assume we have this input video sequence, okay? And in this video sequence, we have two actions. In this case, we have the action horse riding. The images might be a little too small. Embedded inside this horse riding action, there's another action of a person performing cliff diving, okay? And the target of this spatio-temporal task is to say, okay, the cliff diving action starts here and ends there. That is the temporal sort of localization or grounding. And then the action cliff diving is happening at this point spatially, okay? So in a sort of spatio-temporal scenario, we would like to spot both in time and space where the action is happening. And the architecture we use here is is a CNN LSTM architecture. So LSTM is a special type of a recurrent neural network. And the way this works is we feed in frames. If this is time, we feed in frame 1, 2, 3, 4 into a convolutional neural network, in this case a VGG 16. We then have features that describe these frames, and these features are input into this recurrent network in order to predict what action is happening at every point in time. Now, when we perform this forward pass on the pipeline, so we go through the CNN, we go through the RNN, we get class conditional probabilities for what the network believes the action is happening at every point in time. What we do now to perform grounding is we backpropagate a prior probability distribution of what action we would like to ground, or what action we would like to see the evidence of. So for instance, this vector here might be the prior probability distribution for cliff diving. We backpropagate through, again, the RNN and the CNN. However, we had to change the RNN and CNN formulations in order to be to do this specific grounding in a spatio-temporal time. So we had to change the 10H's into ReLUs, for instance, for the RNN, and that changed the backpropagation part as well. We then add also a temporal normalization module in the middle in order to be able to get this grounding result. So the backward pass works as follows. So we backpropagate through space, but then we also backpropagate through time. Okay. We then get maps. So in the same way we got maps for images, we get a heat map on every one of these frames, right? And so if you like, if we backpropagated the prior probability distribution for diving, then we will get heat maps over all of these frames for the action diving. What we do next is we really want evidence that is discriminative to this action diving, right? So, but in neural networks, there are neurons that fire for many things. Like you will find a lot of neurons that fire for animals. They'll fire for zebra, and they'll also fire for elephants because they're both animals, they're in very similar backgrounds, they both have 4 legs, and so there are a lot of things in common between them. What we want to do here is we want to find the evidence of diving, but not anything else, or none of the other classes upon which the network was trained. And so what we do here is we multiply the top layer, the classification layer, of this network, we multiply all the weights by -1, getting like the other side of the hyperplane basically. And then we get the heat maps for all of these frames. We subtract these heat maps from these heat maps, and what we get now is the discriminative evidence for diving. So we get the evidence for non-diving, subtracted from the evidence of diving to get these discriminative maps. So we test these discriminative maps like compared to the normal maps that are not so discriminative, and we see that there is a lot of benefit of doing so. So now, if we assume that we have this heat map on every one of these frames, how can we use that to localize where the action is happening? So you can simply think of it as as a simplified version. You can think of it as a zero crossing of the sum of this map. So if you just sum up the heat maps at every time step and you compute a sort of zero crossing, you can say the action starts here and the action stops there, right? Of course, real data is not this clean, so we had to propose a dynamic convolutional operator that starts somewhere in the middle of the action and keeps growing until it decides that these are the boundaries of the action. So this is a sample result from our work. So what you're going to see here is the same video is going to play on the left and on the right. On the left, it's going to highlight the evidence it sees for the action handstand walking, and on the right, it's going to highlight the evidence it sees for the action ice dancing. So there are a lot of things we can see in these videos. We can see that mostly the action is being correctly highlighted. We can also see the lag So if you've worked with recurrent neural networks or LSTMs, you probably know that there's a lag of a few seconds where the memory resets when it starts, to see a new action happening. And you will see that in the borderline. So we know exactly how many frames this lag is. So you can see there was a slight highlight here on ice dancing, although this is highlighting handstand walking. We know exactly how many frames this lag is, and we can actually, post-process fix it. But these are the raw results of the system. So to conclude this first part of the talk, we are the first to formulate top-down saliency in deep recurrent models for grounding videos. And we do so using a single contrastive backward pass. So all we have to do is go through this LSTM CNN model in a single backward pass in order to get these heat maps and be able to show this evidence spatio-temporally. And although we are not directly optimizing for any localization, so we're just training these models to, classify trimmed actions, right? But we are still capable of performing localization, although we do not really optimize for that. And so on an action detection dataset, where the task is, specifying when an action starts and when an action ends, this dataset is called THUMOS 14. These are all supervised approaches that try to say when the action starts and when the action ends. So they actually optimize for this task. However, our approach does not directly optimize for that task and obtains a very comparable result just by using the evidence that is inside the learned network. This is another application of this work. So what we do in this application is we have an image caption. So this is the image, right? We have an image caption that was produced by, again, a CNN LSTM model. The caption is a man in a lab coat is working on a microscope. What we do now is we probe the network and we start asking questions like, why did you predict the word man? Okay? And this is the answer. So we backpropagate the prior probability distribution of the word man through this model using this formulation, and this is the output. You see the most right value or the highest value on the saliency map is on the man's head, basically. And then when we say, why did you predict the word working, it sort of highlights the bench area. And then why did you predict microscope? It highlights part of the microscope. And so you might have a question as to how do we evaluate these grounding techniques? How do we know they're correct? Well, there are a lot of data sets where a lot of objects are annotated. So what we do in these scenarios is we test the overlap, or basically we have a bounding box around the highest points in this heat map, and we see whether it really overlaps with the underlying object. Good. So now I've shown you what grounding is in images, and what grounding is in videos. Now, what we do next is we say, okay, if we can now ground the evidence as to why a network made a specific decision, or at least focus on a specific subset of the input, how can we use this evidence to further improve our models?
Excuse me?
Yeah.
For that one. So how about if the word is the first A or the word is the second A man?
That's a very good question.
And maps.
Yeah, that's a very good question. So we haven't tried doing this simply because the annotations do not include these words usually. So the annotations are usually nouns, and sometimes, very rarely, they're verbs as well. But most of the annotations are nouns and objects. And so these connecting words are not backpropagated for. But I guess we could backpropagate for this A and see whether they really, whether the language semantically modeled correctly, whether this one will highlight the microscope and that one will highlight the laboratory. All right. So, how can we improve models? So we have two frameworks. One of them works at training time, the other one works at test time. So I'll start with the first one that works at training time. The name of this approach is Excitation Dropout. So we all know dropout. Dropout is a regularization scheme in deep neural networks. And that regularization scheme improves performance. The way standard dropout works is you select some neurons at random, uniformly at random. You decide that you're going to drop the forward activation of these neurons, and you train. Okay? That's how standard dropout works. Now we propose excitation dropout, and we show that this works better than standard dropout and other state-of-the-art dropout techniques. And the way this works is we input an image into this convolutional neural network. We perform a standard forward pass. We get class conditional probabilities, specific class. We also perform a backward pass, but before we perform the backward pass, we have this additional colored loop, okay? Now let's see what this loop does. What this loop does is it backpropagates the ground truth label of this image, and it obtains a specific saliency map, like the saliency maps we've seen before, right? Now these saliency maps are every neuron corresponds to a specific saliency on the saliency map. And what we do there is we drop out with a probability that is proportional to how much this neuron is contributing to the prediction. So if I have a neuron that is contributing to the prediction with a very high probability, I'm going to drop this neuron with a higher probability. And if the neuron is not contributing to the decision, I will not drop it out with a high probability. Now, it might be a little bit counterintuitive. You might say, maybe I would like to drop out the neurons that are not important, that are not contributing to the decision. Why do I drop the neurons that are actually contributing to the decision? Well, our answer is, if you drop the neurons that are contributing to the decision, the network now has a loss minimization function, and it's going to be forced to find alternative routes to the ones you dropped, right? And so in this case, you are regularizing, but you're still forcing the network to maintain this loss minimization. And so we decide which neurons we want to drop based on the saliency map, and then we perform the forward with the dropout, and then we perform the normal backward pass. Now, this colored loop over here only happens in the last fully connected layers. So it's a very light addition. It does not go through all the way, right? It's a very light addition. It could. We show some experiments where it goes all the way back to earlier convolutional layers, but it doesn't have to. So it can be performance-wise, it could be very efficient. So these are some examples on shallow networks showing how excitation dropout performs compared to, for example, the blue curve is curriculum dropout, which is currently state-of-the-art dropout technique. And then we also compare it to the yellow curve, which is standard dropout, and also no dropout, which is the green curve. So these are 4 benchmark data sets in computer vision, and the purple curve shows how excitation dropout performs with respect to these other dropout techniques. Good. So we talked about how we're going to drop some neurons, so we're sort of blocking the path of the network when we drop a neuron, right? But the network is going to learn this alternative path, right? And so what you can think of it is there's some redundancy that's happening, right? The same information is being learned in multiple paths. So we show that this redundancy is actually very useful for network compression, okay? So what we show in this work is the x-axis is how many neurons we drop, right? And then we show that when we use excitation dropout, we can drop more and more neurons, but maintain the performance of the network. And that's because of this encoded redundancy that has been implicitly learned in during the training process. The second framework that works at test time, that uses explainability in order to improve model performance, we call guided zoom. Now, this is how conventional CNNs work for images. You input an image into the conventional CNN, you get class conditional probabilities. You say something like, with highest probability, this network, so this is just a cartoon example, that with highest probability, the network thinks this is a car, and with the second highest probability, the network thinks this is a motorcycle, okay? Now, in this case, the top 1 accuracy is 0, because it incorrectly classifies the image. The top 2 accuracy is 1, because it correctly classifies the image within the top 2. Now, the top k classification accuracy is usually significantly higher than the top 1 classification accuracy in images or in computer vision. And this is specifically more evident in what we call fine-grained data sets, where the differences between the classes is quite subtle, like different kinds of bird species, right? I'm going to show an example where you have like 3 different types of bird species. They all have yellow and gray. They look really similar. It takes like a lot of effort to differentiate them. And so one example of a data set has a top 1 accuracy of 86.9%, but then it has a top 5 accuracy of 98.9, which is significantly higher. And so what we try to do in this work is we try to use this top K accuracy in order to boost the top 1 accuracy, right? And so what we ask the network is the following question. We say, okay, why do you think this is a car? We get the evidence or the patch of the image that is the highest evidence or that is mostly contributing to the decision car. And this is the patch in this case. Why do you think it's a motorcycle? And we get the patch from the image as to why the network thinks this is a motorcycle. What we do now is we ask whether this evidence is reasonable for a car or whether this evidence is more reasonable for a motorcycle, right? So we now, instead of like comparing images or having the network classify images, we now have a new module that sort of compares and tries to classify the evidence itself, right? And the way it does that is it was trained on evidence of many cars in the training data set, right? And then we can now input this evidence of car, input this evidence of motorcycle, and see which one is more reasonable compared to the evidences that were used at training time. This evidence CNN is going to make a prediction. We're going to combine the prediction of this evidence CNN with the prediction that was originally made with the conventional CNN on the entire image. So if you like, there's a prediction on the entire image, and there's also a prediction on the evidence. We then input this to a decision refinement module that would hopefully, select the correct class within the top K, and in this case would say it's a motorcycle. Okay, so the question now becomes, how do we train this module to classify the evidence, right? So what we do is we extract an evidence pool, and this evidence pool is based on evidence patches from the training data. And so let's say in this first scenario, we have this BERTS data set. It's called COOP200, a Stanford data set. And these are 2 examples of patches of evidence that were extracted from these 2 classes of this data set. So you can see that the evidence is quite coherent between these different images for this specific bird species and also for this yellow-headed blackbird. These are examples of dog classes in the Stanford dogs dataset, and these are examples of evidence of 2 models of aircrafts. Now, all of these patches could be used to train this evidence CNN. But we don't just use this evidence, the reason being the following. Let's take the example of the dogs dataset. You see that the most discriminative evidence in every case is always the dog's face, right? But that's only because the network focuses on the evidence that is most discriminative, right? So if this part is sufficient for the network to make a decision or a correct prediction, it will just use that part. However, there could be other parts, like the second most discriminative evidence or the third most discriminative evidence that could also be really helpful in a prediction. And so what we do in this case is we use the adversarial approach that we et al. Introduced for image segmentation. We use that approach to get more evidence or secondary and tertiary evidence. So for instance, if we have this image of a flying bird, first we compute the evidence that the network used to make a decision. In this case, it's the bird's head, right? We extract this patch, we put it in the pool. But then what we do is we block that evidence, and again we ask the model, what evidence remains for this specific bird species? And then it highlights the tail, right? We take this patch, we also place it in our training pool, and we repeat the process again, and the third most discriminative evidence in this case is the wing. We also extract that and so on. So we use an L equals 2, which means we always extract like 3 patches for every specific image. And we use all these extracted patches as training for our evidence CNN. So this is an example of some patches for 3 dogs from the Chihuahua class of the Stanford dogs dataset. And notice what happened here. When we asked the model for the most discriminative evidence, it was always the face of the dog. And then when we block that and we ask the network, now what is the second most discriminative evidence, the network always chose the ear of the dog for this specific class. And then when we did the third round, it chose the legs or body parts of the dog, which indicates that there is this implicit part localization that is happening within the network in order to be able to perform this classification. And so by doing this iterative adversarial erasing, we're not just getting this implicit part localization, but we're also getting implicit part labeled localizations, because now all of these patches, we can assign the label Chihuahua to them, and we would then get this sort of correlation between the different parts and the label. We trained the evidence CNN for the same classification task, but on this pool of generated evidence. And at test time, we predict the class of the evidence. We combine that with the prediction of the conventional CNN, and then we get a refined decision. So let me show you an example of how this works. So we have an input test image, okay? We get the highest class conditional probability B.4 for this class, okay? However, this is not the ground truth class, although we get the highest probability for it. The correct class has a probability of 0.3, so the one highlighted in blue is actually the ground truth class. Now, this is the output that we get if we use a vanilla CNN. However, if we use our approach, what's going to happen is this evidence over here, which is like a zoomed-in approach. That's why we call it guided zoom. And so we compare this with the evidence, or we don't directly do that. The evidence CNN module does that. It compares this evidence with all the different evidence that it has for other samples of these ground truth classes in the training data. And so now, when this is compared against these, it's a lot closer than when this is compared against these two. So you can see some changes. The colors are similar, but there are some differences in texture between the images of these two different classes. So, how much does this approach improve models? So we used for these experiments, a vanilla ResNet 101, okay? So a ResNet with 101 layers. And this was the classification accuracy on 3 data sets, 3 fine-grained data sets. And this is how the top 1 accuracy improves when we use our approach at test time. So, for example, for the COOP data set, 82.3 is the result, and then it becomes 85.4 when we employ guided zoom. And so to conclude this work, we were able to improve the top 1 classification accuracy for fine-grained data sets in a weakly supervised way without needing any part annotations, hierarchical label information, or any additional web crawl data, and so on. So this concludes, I think, the 2 frameworks I wanted to show you that utilize this sort of grounding in order to improve model performance, either at training time or at test time. And in our lab, we currently are interested in other approaches as well. So for instance, when I get a grounding, let's say we have a surfing action, a person performing surfing. And we have one grounding technique that highlights the person performing the surfing action, and then we have another grounding technique that highlights the waves, right? Now the question is, which one of these grounding techniques is correct, right? And the answer will probably depend on the data set. So let's say the data set only had one action that involved waves. And so the grounding algorithm that highlighted the waves probably has a point, but it's not highlighting the action. The person performing a surfing might just be, in a posture that's very similar to a person who's standing up, right? So we're doing some other research to see how these groundings model human perception of evidence in images. So we try to ask humans to highlight what they think is the evidence for specific actions, and we're trying to see whether this maps to what the model also thinks, and vice versa, showing evidence of model to humans and seeing whether humans are capable of understanding how the model is performing such explainability. And yeah, thank you. I'm happy to take any questions.
Yeah, we may have plenty of time for questions. Do you think your classification model is more resistant to adversarial attacks?
Actually, that's a superb question. So yeah, so we have some work that we do have on our webpage where we actually use this for adversarial attacks or adversarial defenses, and we show that we are capable to have a stronger defense if we train in this specific way. We're also interested in other similar work, as in can we have watermarks based on this saliency approach. So when I train my model, if I use a specific data set, and this data set is not for commercial use, right? This data set is just for academic use. Can I sort of watermark the images in this data set such that if any other company uses this for commercial work, can I know that whether their model used this data set or not, right? Using these sort of saliency.
Does the model works for fine-grained classification?
Yeah, the last.
So for example, you kind of grounded it on some special locations, but to kind of differentiate this is between different kinds of birds, you actually need to go down much more fine-grained than that.
Yeah, so we actually don't specify like which parts. Like we don't say that we want to highlight the beak of the bird.
Yeah.
We just say we want to highlight the evidence that the network would use to classify this image into this specific bird species.
And you leave it to human to make a decision.
Exactly. The
So it's kind
network
of
makes the
guided.
decision without any guidance.
So it's kind of guided expert.
Yeah.
Okay.
So regarding to that's intuition, probably one way just get a small area actually we remove all the other noise from our perspective.
Yeah, so it's very useful in applications like fine-grained classification, but actually for other applications, guided zoom might hurt on its own. Like if it's used on its own without looking on, like if you use the evidence and ignore the actual image, it might hurt. So a soccer ball might be, a soccer ball always appears on a green pitch most of the time, right? And so if you see the green pitch, you have like support, right? If you see some of the background, you have support for the evidence for the correct class. And so, yeah, it's a little bit application dependent as well.
Okay, kind of a balance of the global feature.
Exactly.
Any more questions?
So your method will only look for kind of high attention kind of patches.
Correct.
So supposing, I don't know, I can't think of an example, maybe something you're looking for is not of a high attention patches, and then how do you, would your method just kind of miss that altogether?
So what will happen in this case is the high evidence patch, the evidence is sort of tied to the prediction, right? So if you find an evidence for a specific prediction, you take that evidence, you compare it with all the other evidence you've seen during the training time, it will either be coherent or it will not be coherent, right? And so if it's coherent, our assumption here is that the evidence prediction pair is reasonable. That's the assumption of this work. So we're assuming that the evidence in the training data is capable, or comparison against the evidence in the training data allows us to perform such. Yeah, that's a good question. That is an assumption of the work. Yeah. Yeah.
In the example of, caption to image, so
Yeah.
that example is perfect. Okay, for every noun phrase you can find a very good explanation. So this test scope that
Yeah.
are.
So we actually
is
estimated the art
it-
results on.
Is it easy to find such an example? Or, how about a portion of words that can find satisfactory correspondence in the image?
Yeah.
So how about that?
Yeah, that's a good question. So we do. Our system does make mistakes. This was a good example that you've seen. So our system does make mistakes. However, it also has state-of-the-art results on caption evidence grounding. So on the Flickr, we use the Flickr 30K dataset, where we try to ground the locations of noun objects in the images, and we do have state-of-the-art results to date.
I have another question. So,
Yeah.
can this technique help us to improve the training set? For example, in some scenario, we may have maybe two dots in the big training data, but both of the dots are just on some each. So if we use this technique, maybe you find that the evidence is not the dot itself, it's just the each. So then probably we can find this type of phenomenon. And we realize, okay, we need to do more labeling and improve the data set. And then finally we can improve the whole system. Yeah, that's cool.
Yeah, that's super cool. So, we currently are working on a project where what we do is we involve the human in the loop in this XAI system.
Yeah.
And what we do is we show the evidence to the human. We ask the human, is this reasonable evidence? And then they say yes or no.
Okay.
And then if they say yes, what we do is we reinforce the evidence that we have, the heat map basically. And if they say no, we suppress the heat map. So we use, like the simplest option is like 1 minus the saliency, right? And then we use that in training. So we use the human feedback to alter the weighting. So
Yeah, I think that's if we can do this systematically, probably
That's
we
awesome,
can improve the whole system much better.
thank you very
Okay, if we do not have more questions, so maybe we can say sorry again. Okay, so our next speaker will be Professor Shou Wang from the Tsinghua University. And,